So previously I mentioned that heat and work are the mechanisms in which energy is able to transfer from its system to its surroundings and vice versa. Let's now go into detail about each of these phenomena. All right, we'll begin with heat. All right, and so whenever we talk about heat in an engineering context, what we really mean is heat transfer or heat flow. Okay, and so heat typically refers to heat transfer or heat flow. Okay, all right, and so this phenomena is inherently complex, right, and deals with a lot of kind of detailed math. Right? We're not going to cover that math in this course, but you will soon enough. In fact, you'll learn about the microscopic physics of heat transfer in your transport phenomena in thermodynamics courses. Okay? And so those will be in the fall semester of your junior year or third year in the major. Okay? So we won't go into that quite detail of heat, but you will use the concept of heat in order to close your energy balances in this course. Another thing I want to emphasize about heat is that it's not a substance. In fact, put this in all caps, is not a substance. And so what I mean by that is whenever you refer to heat, you can never say that you have this much heat, right? This system contains, 30,000 joules of heat, right? Because, a system can't contain it, right? Heat is not an energy, it's an energy transfer or an energy flow. And so a system can't contain heat, merely heat can flow from a system to its surroundings or vice versa, right? So heat is only referring to the energy flow, right? The amount of energy that moved from the system to its surroundings. Okay? All right, and so heat is not a substance, it's an energy flow or an energy transfer. And the sign and magnitude of a heat term are going to depend on how you define the boundaries of your system. So sign and magnitude of Q depend on system boundaries. All right. To illustrate this concept, I want to go through an example that involves a pizza. Okay? And so what I'm drawing here is an oven. Right? And in this oven, you're going to have, I don't know, like a DiGiorno pizza or something. So pizza. Or whatever brand of pizza you like. Okay? And so in this oven, you place the pizza. And initially, before you put it in the oven, the pizza was at room temperature. You let it heat, kind of warm up a bit to 72 degrees Fahrenheit. Now, the pizza was at room temperature, but you then place the pizza inside a heater, or inside an oven that was preheated, okay, to a much higher temperature, 400 degrees Fahrenheit. Okay? Now, so what we have here is a relatively cold pizza that was placed into a relatively hot oven. Right? And so let's think about what the heat flow or the heat term would be in this sort of system. All right? And so in order to determine that, we first need to define what our system is. And so we have different sorts of choices here. Right? Our first choice could be that our system is just the pizza itself. All right? And so if our system is the pizza, what we have is a cold pizza initially that's placed into a hot oven, right? And as you'll learn in your thermodynamics course, is that heat will travel from hot things to cold things, all right? And so, in this case, if we define the pizza as our system, that would mean that the heat flow in our system would be positive. It'd be greater than 0. And that's because if the pizza is our system, heat would travel into it from the surroundings in order to heat the pizza up to cooking temperature. All right. So if the pizza is a system, Q is greater than 0. But now let's consider another case where instead of defining the pizza to be a system, we instead define the entire oven to be our system. Okay? All right. And so in this case, if the oven is the system, our Q is going to be different. And that's because, let's consider let's assume that we have a really nice oven, right? That's well insulated, right? So that if you're standing right next to it, it doesn't feel that hot, right? And so if that's the case, the oven, everything inside the oven is going to be our system, and everything outside is the surroundings, right? And so if heat can't travel into or out of the oven, what that means is that the Q for our system is then going to be equal to 0. All right? And so depending on how we define the system, whether it's a pizza or whether it's our insulated oven, that's going to affect what our Q value is. Okay? Extending on the point, or the case where, if the oven is our system, Q is equal to 0, another way we describe that sort of scenario is that it's an adiabatic process, okay? Or an adiabatic system. And so if we have an adiabatic process or system, what that means is that our Q term is equal to 0. Okay? And so some hints for having an adiabatic system is if your system is well insulated. And so whenever you see the words well insulated, what that should mean to you is that heat cannot travel into or out of the system. All right? And so if heat can't travel into or out of the system, that means that the heat flow has to be equal to 0. Okay? So that's a sort of system that you're going to encounter quite a lot throughout your career, or especially in these courses. All right, another sort of scenario I want to define for you is an isothermal process or an isothermal system. All right, in an isothermal process, all that means is that the temperature of your system at the end, your T final, is going to be equal to whatever the temperature was at the beginning, your T initial. Okay? And so some key words to always look out for are the words isothermal and adiabatic.